Introduction. This textbook is prepared for those who want to know more about technologies supporting Foundation Fieldbus and function blocks. Yokogawa Electric Corporation and its group funded this textbook to encourage Foundation Fieldbus adoption by as many people as possible. No commercial ambitions are in this book. This textbook is a tutorial on Fieldbus technologies and does not intend to override any technical content of Foundation Fieldbus. If this textbook contains any explanation that conflicts with Foundation documents, the Foundation documents are correct, and such conflict should come from an error of explanation of this textbook or this textbook failing to follow the technology update of Fieldbus Foundation. The authors want readers to use this textbook to become more knowledgeable about Foundation Fieldbus and apply it to their industrial projects. Fieldbus is the language of the 21st century. What is Fieldbus? Fieldbus Foundation defines Fieldbus as a digital, two-way, multi-drop communication link among intelligent measurement and control devices. It is one of several local area networks dedicated to industrial automation. Modern industries could not survive without information technologies and networks in the 21st century. From production lines to enterprise levels, digital communication supports all economic and social activities with its latest and powerful technologies. Fieldbus is a part of it and cannot be separated from others. Fieldbus is the lowest level in the hierarchy and exchanges information with higher-level databases. We have standards to transfer measurement and control data between the control room and the plant floor. They are pneumatic and 420 milliamp electric signals. We have enjoyed their finest features of interoperability and easy maintenance. Smart communication, introduced in the mid-'80s, opened an era of digital communication, but it had many limitations, such as proprietary protocols, slow transmission speed, and different data formats. The idea of Fieldbus was proposed to solve such problems. A standardized digital communication for industrial automation is changing the production system very quickly. Fieldbus benefits. Fieldbus is expected to reduce the lifecycle cost of the production line and then the total cost of ownership (TCO) of the plant. Planning phase. Fieldbus allows you to integrate your plant assets on a single plant automation system on digital communication networks. You can connect devices from multiple suppliers without custom software, and these network-based systems allow for smaller control rooms, smaller cabinet rooms, and more information productivity. Installation phase. Fieldbus offers reduced installation and material cost by replacing the traditional one-to-one wiring scheme with networking or multi-drop configuration, while intelligent field instruments make commissioning and plant startup much faster and less expensive. Operation phase. Fieldbus integrates various installations of control functions into one system to effectively optimize control of your plant. In addition, a unified human-machine interface, HMI, is provided for your operation. Function blocks allow control functions to migrate into field devices, allowing control functions to move to the field. Maintenance phase. Fieldbus allows for the reporting of self-diagnostics, calibration, and environmental conditions of field instruments without disturbing the plant control. Since it uses intelligent instruments, your stock for spare or replacement instruments can be dramatically reduced. Software packages for asset management are useful to minimize maintenance costs. Renovation phase. Enhanced functionality of field instruments is endless. Fieldbus devices are becoming standard off-the-shelf instruments, which make it very cost-effective and easy for you to extend the life of your plant. By simply connecting a new device, you can immediately benefit from advanced functionality. Upgrade costs can be reduced because network-based systems are modular, which means they are done online. Foundation Fieldbus. Fieldbus is not a product, but a technology to make the above benefits available to end users. The following two conditions are necessary to make them come true. Many vendors provide Fieldbus instruments. Those devices are interoperable. Fieldbus Foundation was established in 1994 to achieve these goals. Its major activities are to promote a single international Fieldbus to both users and vendors, to deliver Foundation Fieldbus specification, to provide technologies for Fieldbus implementation, including education, and to install an infrastructure to achieve interoperability. Foundation Fieldbus is a subset of IEC standards, IEC 61158, and ISA S50.02. Fieldbus Foundation and its members adopt Foundation Fieldbus as an enabling technology to utilize it to bring the above benefits to end users. OSI Reference Model. Communication specifications are often explained with reference to the Open System Interconnect OSI layered model. Foundation Fieldbus is specified according to the simplified OSI model, consisting of 3 layers: physical PHL, data link layer, DLL, and application layer, APL. Layers 2 to 7 are implemented mostly by software and are often called the communication stack. Fieldbus Foundation specifies not only communication, but also some user applications, which use Foundation Fieldbus communication, though the OSI model does not specify any user application. The application layer of Foundation Fieldbus consists of 2 sublayers: Fieldbus Access Sublayer, FAS, and Fieldbus Message Specification, FMS. FAS is the glue to map FMS services to the data link layer. Protocol Data Unit. Each layer appends layer control information called Protocol Control Information, PCI, and more information to the message of the higher layer. A data unit exchanged between the same layers is called Protocol Data Unit, PDU. A PDU may contain optional data called Service Data Unit, SDU, which is a PDU of the next higher layer. A communication layer exchanges other PDUs without SDU to perform its functionality. Communication through VCR. Messages are exchanged between applications sitting on the Foundation Fieldbus. When a message is transferred, it goes down through a channel called Virtual Communication Relationship, VCR, to add PCI before it goes to the wire. At the destination, it goes up through the partner VCR to the receiving application. PCIs are appended and removed when a message goes through VCRs to allow layers to perform their specific functionality. A Fieldbus device has many VCRs so that it can communicate with various devices or applications at the same time. It is possible because the VCR guarantees the message goes to the correct partner without risks of losing information. A VCR is identified by an application with a device local identifier called index, specified in the application layer. It is also identified from other devices with DL address specified in the data link layer. Physical layer. 31.25 kps physical layer, 31.25 kbps. Physical layer is the most common since IEC and ISA approved it in 1992. This textbook explains only wire medium, but optical fiber can be used as an alternative. Though 31.25 kbps sounds slow compared with the latest telecommunication technologies, it is necessary to replace traditional 4 to 20 milliamps analog transmissions. It is intended to apply to field devices for various environments of industries. Many users want to enjoy the simple installation of 2-wired transmitters. Explosive gases prevent high-performance electronics in the hazardous area of the plant. Transmission of 31.25 kbps was chosen for those applications which demand devices of very low power consumption. A field device can draw electric current from the medium to feed energy to its electronics. It is called a bus-powered device and is the Fieldbus equivalent of 2-wire installation. Signaling method. Fieldbus utilizes a similar technology for smart transmitters to transmit an electric signal to the wire. The supply voltage is applied by a power supply through an impedance conditioner, typically consisting of inductors. DC current through the impedance conditioner feeds devices. The impedance conditioner makes the output impedance of the power supply higher than 400 ohms in the signal frequency bandwidth. Each cable end is terminated with a terminator of 100 ohms impedance. It makes an instrumentation cable a balanced transmission line so that a signal of relatively high frequency can be transmitted with a minimum distortion. Wiring rules. The IEC-ISA standard specifies minimum amplitude and worst waveform of a received signal at a device at any place of the Fieldbus network. The physical layer receiver circuit must be able to receive this signal. You can configure the transmission line in any way as long as the received signal quality is guaranteed at all receiving nodes. However, it is not always simple and easy. Instead, the ISA SP50 committee created a set of wiring rules to simplify the network design. The received signal is always of better quality than the minimum requirement if the Fieldbus is designed according to these rules. They sound a little conservative, but are useful to design a workable network very easily. Rules: 1. Number of devices on a Fieldbus is between 2 and 32. 2. Cable is a twisted pair of individual shield type A with 18 AWG wires. 3. Overall cable length does not exceed 1900 meters. 4. Overall spur length does not exceed 120 meters. Maximum number of devices decreases according to the spur length as shown in the table A-1. 5. When you use multiple twisted pairs with overall shield type B with 22 AWG wires, the total length decreases to 1200 meters. IS consideration. Intrinsic safe IS installation is important for plants where explosive gases exist. IS is the rule to design and install devices in a hazardous area to prevent an explosive gas being ignited by electric discharge or the surface temperature of a device. An IS field device must be carefully designed to prevent ignition even when a single failure of its component takes place. An IS barrier must be installed to separate the hazardous area from the safe area. A barrier strictly limits the voltage, current, and power fed to a device installed in the hazardous area. Devices and barriers must meet the same design criteria provided by safety organizations, IEC, FNLEC, PTB, etc. Medium access control. The most important functionality of the data link layer is medium access control, MAC, of the Fieldbus. Since all devices on the same cable receive the same physical layer signal, only one of them is allowed to transmit a signal at a time. MAC is the method to achieve this goal. The domain of devices sharing the same physical layer signal is called a link. Only one device on a link is allowed to use the medium, physical layer at a time. Link Active Scheduler, LAS, has the role of controlling the medium access. The right to send a PDU is called a token. The LAS possesses the token and gives it to another device to allow it to send messages. The token is then returned to the LAS for further medium access control. Data link layer provides 3 levels of priority: urgent, normal, and time available, in this order. An urgent message is transmitted immediately even when other messages of normal or time available priority are in the waiting queue, and vice versa. Addresses. Communication partners in the data link layer are identified with DL address, which consists of 3 components: link, node, and selector. The link field consists of 16 bits and identifies a link. This field is necessary when a message is going to other links through bridges. The node field gives the node address of 8 bits. A foundation device has a node address in the ranges between 0x10 and 0xFF, which is classified into LM range, basic range, default range, and temporary range. The selector field gives a device internal address of 8 bits to identify a VCR. When a VCR is connected to another VCR, it is identified with DLCP, Data Link Connection Endpoint, shown in this field. When a VCR is not connected to any others but open to send-receive messages, it is identified with DLSAP, Data Link Service Access Point, shown in this field. Link Active Scheduler, LS, controls the medium access. Foundation devices are classified with device classes: Basic, Link Master, LM, and Bridge. A LM class device can work as the LS, while Basic class devices do not. A Bridge class device has, in addition to LM capability, the functionality to connect links. One and only one device in a link works as the LAS. At least one LM or Bridge class device is needed in a link. LM devices try to acquire the LAS role when no LAS exists on startup or when the current LAS fails. The LM device with the least node address wins this contention. Other LM devices observe the LAS activity and take over its role when LAS goes away. Scheduled communication. The LAS is responsible for scheduled communication, which is necessary to link function blocks. Function blocks are distributed applications operating in a synchronized manner. The LAS manages the communication part of the synchronized data transfer. When the time of scheduled communication comes, LAS sends compelled data, CD, PDU, to the publisher DLCP. Publisher is expected to transmit data transfer, DT, PDU stored in the data buffer of the DLCP immediately. Unscheduled communication. Other communications take place in an asynchronous way. The LAS is responsible for giving all nodes on a link a chance to send messages. The LAS gives a token by sending pass token PT PDU to a node. When the node does not have messages of the given or higher priority to be sent, or the given time interval is expired, it returns the token as return token RT PDU. The LAS controls the message transfer by updating the priority. A device must return the token within the time interval given in the PT PDU. Link maintenance. The third role of LAS is to maintain the link. The LAS gives the token to all devices detected by the LAS. When a new device is added to the network, it must be recognized by the LAS and entered into the token rotation list called live list. The LAS sends a probe node, PN, PDU to node addresses where a device was not found before. When a device is removed from the link, it does not respond to PT anymore. The LAS detects this and deletes the device from the live list. Whenever a change is detected in the live list, the LAS broadcasts the change so that all LM devices share the latest list and are ready to take over. The LAS also broadcasts its data link time, LS time, to the link in a predefined interval so that all devices on the network share the same time, which is necessary to start function blocks. Tabash Data Link PD, Table A3 summarizes data link protocol data units in Foundation Fieldbus, EC established connection, DC disconnect connection, CD compel data, DT data transfer, PT pass token, RT return token, RI request interval, PN probe node, PR probe response, TD time distribution, CT compel time, RQ, round trip time query, round trip time response, CL claim LAS TL transfer LAS, idle.